Hey everyone, this is Dr. Anna, and we are at segment 6 of the Geologic time module in the historical geology sequence at Virginia Western Community College. So let's continue with the radioactive isotopes, which we use for dating geologic events. Some of the elements, especially the ones between 84, so from polonium to 92, like uranium, have really long half-life, so long actually that the elements haven't even decayed completely since they were formed. The systematic analysis of the abundance and half-lives of these isotopes provides information about the age of the universe, the earth, and its rock formation. So that's what we're going to talk about now. So these are the elements we can use for this kind of age measurements. So let's talk about the geologic clocks. Each radioactive element decays at its own constant rate. This is really important. Whatever you have heard, because some people who do not believe that we can uh, measure age of rocks based on the radioactive element, so they will say that this is not true. But it's extremely important that you understand that it is true, because if they use it in the nuclear medicine, like people getting sick and then they are being healed by these radioactive elements, and we know that they are decaying at constant rate, and that's how we use them. Why wouldn't it work for the geologic clocks? So once this rate is known, geologists can estimate the length of time over which decay has been occurring by measuring the amount of radioactive parent elements and the amount of stable daughter elements. Imagine that you have a crystal, like a K feldspar crystal, in which we measured the radioactive isotopes. So at the formation, let's say it had 10,000 radioactive atoms. And after one half-life, there will be 5,000 parent, and 5,000 daughter. So you see, that's how we know that it's one half-life. So if we know the decay rate, then it's easy to calculate the age. As you can see, everything is going to be in that crystal. If it's not weathered, it's really important, and I will talk about that later, that the crystals and minerals we're using for radioactive age dating has to be the least weathered ones, because when there is weathering, then we can lose either one, the parent isotopes or the daughter isotopes. It's easy. So we have to be really, really careful, and we have to understand the possibilities of errors in these samples. So what is the half-life? I've been talking about it, but it's important that we finally know what it is. It's right here. So each radioactive isotope has its own unique half-life. It's very, very important. Own unique half-life. Half-life is the time which takes for half of the parent radioactive isotopes to decay to a daughter product. So half of the, like if there was 10,000 radioactive element originally in the sample, then the half-life will be the time during which the 5,000, so the half of the original 10,000, 5,000 will decay. Okay, that's the half-life. Now, what is really important about the half-life is that it's independent of the physical state. It doesn't matter if it's solid, liquid, or gas. The element is in that state. So it doesn't matter if the element has the physical state of solid, liquid, or gas. It doesn't matter. It doesn't matter what is the temperature. It's absolutely independent. You know, some chemical reaction, for example, the dissolution of salt in water depends on the temperature, but the radioactive decay is not. It doesn't matter what is the temperature. It doesn't matter what is the pressure, because it's a first order chemical reaction. So it's absolutely independent of the temperature, pressure, the chemical compound in which the nucleus finds itself, and essentially any other outside influence. It is independent of the chemistry of the atomic surface and independent of the ordinary physical factors of the outside world. The only thing which can alter the half-life is direct nuclear interaction with a particle from outside, For example, a high energy collision in an accelerator. So no any other way can change the half-life. And every single radioisotope has its own unique half-life. Not two isotope has the same half-life. Every single isotope will have a different half-life. So this is very important that you understand that. So how do they determine the half-life of a particular isotope? Nuclear physics leads to the prediction of the value. However, experimental evidence is needed to confirm that the theoretical time is accurate. We use mass spectrometer. It's a very, very complicated machine, and I had the luck to work with them because I took a isotope geology class at Virginia Tech, and I worked with mass spectrometer. They usually in the prep room they create a very, very pure sample with a known number of atoms. And the sample is placed in a controlled environment for years or even decades, and the number of decay events is recorded. So that's how they calculate the half life of all the isotopes. In this way, the half-life of many isotopes is known to a high degree of accuracy, and the mathematical models are confirmed. So we know that whatever I said right before is true. Additionally, the theory is also confirmed using spectroscopy of the supernova, especially for shorter half-lives. And this here just shows you the mass spectrometer. It works with magnets, and actually it can separate different isotopes. For example, if you put uranium sample in it, it will separate the 238, the uranium 238 and the uranium 235. So it's very small mass differences which the mass spectrometer can completely separate. So it's really cool. So the magnetic field will separate the particles, and it's based on the mass charge ratio. And these are the radioactive elements we use in geology for uh, ages to calculate ages of different rocks. So these are, of course, I will not ask it because I don't know, but here is the radioactive parent, the stable daughter, and the half-life. See, we use a lot the uranium 235, the 238, carbon 14. But of course, we will talk more about it because look at the half-life of the carbon 14 is 5,730 years. So it's very, very short. But look at the thorium 232, it's 14 billion. Remember, the Earth is just 4.6. And look at a lot of these elements are decaying into lead, like 206, 207, and 208. Okay, this is the mathematical expression that relates radioactive decay to geologic time, and it is the have this is the equation to calculate the age of the sample, and the lambda is the decay constant, which is given, and then the daughter and the parent. So the daughter over and the parent under. So this is the equation. I will not ask it. You do not have to use it. It's we're gonna use the carbon 14 curve to do the calculations in lab 2. Okay, so that's just how the curve looks like. So what kind of rocks are used most commonly for age dating? I already mentioned it to you that the igneous rocks are the best. The dates they give indicates the time at which the magma cooled and solidified. As it cools, the newly formed crystals may contain some radioactive elements as straight elements, such as potassium 40 or uranium 235 or 237. And the potassium 40 is mostly found in potassium feldspar, the K feldspar, muscovite, or amphibole. Uranium may be found in zircon or K feldspar or monazite, apatite, or sphin. Sphin is amphibole. The radioactive elements tend to become concentrated in the residual melts that form during the crystallization of igneous rock. So the last minerals which are crystallizing, and the K feldspar is one of the last ones. Zircon as well. The amphibole, monzonite, these are like accessory minerals, and they are about the last to form. So most of the time, the felsic rocks are the best, such as granite. We get the best, most accurate ages on the granite rocks. So wherever there is granite or age is going to be much better than other igneous rocks. Of course, they are okay, but but the granite is the best because it has all the radioactive isotopes in the K feldspar and zircon and those minerals. So this here is the half-life curve. When you're doing the half-life curve, what you have to do is put the 100%, like if you have 100 uranium-235 atom in the K feldspar, then this is right here, and then down here you put the half-lives. And we know that the carbon 14 has a half-life of 5,730. I already pointed it out for you. So we know that one half-life is 5,730, two will be twice as many, three will be three times as many, and so on. So it's not that difficult. So on the x-axis is going to be the half-lives, and on the y-axis is going to be the number of atoms. So it's simple. You just say that at 50% is going to be the first half-life, because during the first half-life, half of the radioactive elements decay. But during the second half-life, half of the half will decay. So that's how it goes. So it's 25% right here, and then 125 right here, 0.62.5, and so on. Now, what is really interesting on this curve, I want you to realize that when you already had 10 half-life, basically like unmeasurable amount of radioactive isotopes left. So after 10 half-life, which is in the carbon 14, like this one is the carbon 14, C14. When you have like 10 half-life, which is 57,000 years, you cannot measure any leftover radioactive elements. So if somebody comes to you and says that I measured this sample and it's a million year old and I use carbon 14, then you know that they are not telling you the truth. Because after 57,000 years, the carbon 14 is not reliable. Also, if you look at the very beginning, like right here, you don't have enough decayed carbon 14 atom, so you cannot really tell. So somebody tells you that this thing was like 200 years old, and you know that it was 200 years old, and you put it in the mass spectrometer, you will realize that in 200 years, you just don't have enough daughter product to be able to measure. You see what I mean? So you always have to kind of know what can you measure and what can you not, and what kind of radioactive element you want to use to measure. Like right here, you can see the carbon 14 is 5,730. So you cannot really use it after like 70,000. So I would go from about 5,000 years, probably 2,000 years, to 57,000 years. That's the range where it could be used. Same with the uranium 235, let's say the 235, 700 million years, so zero point 0.7 billion. So if I wanted to measure a sample with the age of like 500 million, like Cambrian or so, if you already learn your time scale or you're learning it as we speak, then it's good. But if you want to measure like a 50,000-year-old sample, it's definitely not good, because you won't have enough lead-206 to measure and be able to calculate the age. So it's very important that you understand what kind of elements can be used for what kind of age range. So you have to have some kind of idea to figure out what to use. So now this is really interesting that when you start with a, let's say, a uranium 238, it's not going to be just one decay to make it into lead, which is the final product, which is not radioactive anymore. Most of the time, there is more than just one step. Like here we are. Here is the uranium 238. It goes with an alpha decay and will become thorium 234. But if it has a beta, like it's gonna have a beta decay to the protactinium, so therefore it's gonna stay 234. So it has to have another alpha to go down, because we have to go down all the way to 206. You see the lag. And we start with 238. And the alpha decay is taking off 4 from the mass number. So that's the only way that it can go down. Any beta decays really do nothing. Beta, beta, You can say there is a whole bunch of them. So the only thing which takes down the mass number so it gets closer to the lat 206 are the alpha decays. So it will take forever for these things to go. Most of the time, just the first from the uranium to the thorium is what 4.5 times 10 to the 9, I think, years, the half-life. So usually all the others are very short. So you see, this is interesting that you need more than just one decay to make the final product, which is not radioactive. The Lat-206 is not a radioactive isotope. Let's talk about the problems we might have with these dates. First of all, when we use the igneous rocks, the date the minerals will show actually is the so-called blocking temperature. That's the time or temperature when the mineral becomes unchangeable, which means no more radioactive element will come from outer source and none will leave the system without decay. So that's the blocking temperature. Sometimes when you have a metamorphism afterwards, pretty high temperature can be a problem. Elements most likely are in K feldspar or zircon, those last minerals which are crystallizing. So sometimes the metamorphism can have a temperature which might melt those out. In that case, the clock can be restarted, which means you're not measuring the original age of the granite, but you're going to measure the time for the metamorphism. The timing should be done based on the half lives. I already kind of talked to you about this, that depending on what kind of rock age you might have, you have to use different radioactive elements. Okay, so the carbon 14, as I already told you, should not be used more than 53, like 70,000 is the max. Now, the other really important thing which can mess up the radioactive dating is if you use a sample which has a lot of weathering, especially during chemical weathering, you might lose some parent isotope and might gain some daughter isotope even just in the lab. If the sample is not absolutely clean, then you might get lead contamination in it, which will show like an older age because you have more of the daughter product. So it's very, when I worked in the mass spectrometer, the lab in which the machine is standing is worse than when you go to a hospital in the surgical room. You have to change your outside clothes because lead is a very common element and that is the daughter product in these samples, in a lot of samples. So it's extremely important that the lab has to be absolutely perfectly clean. It's much cleaner, as I said, than any hospital rooms. And the samples preparation is extremely important and you have to throw away every very valuable mineral because it just could be contaminated by the common lead, we call it. So these are very, very important. So when you measure, of course, one sample is not going to give you good time. So therefore, you have to measure a whole lot of them. And when you give the age, it, let's say 1.05 million plus minus 10,000 years. If you don't have the error in it, this is the error. That means that the age data, what you're getting, has that kind of difference, is about 10,000 years. If you say that the sample is 1.05 million years plus minus 200,000, that's not a very good measurement. So the error, without error, the measurement doesn't count. It's, you cannot say that, oh yeah. No, you have to ask what is the error in the data. And then that just means that the data can go in between those. So you don't have two exactly the same measurements. There could be an error in them, like 10,000 years. It shouldn't be really big because then your data is just not good. If you're gonna use something like this, you will have to learn much more about this. But for starter, this is how it goes. So you cannot really trust any data without the error, the plus minus. And of course, every machine has to be calibrated to the standard. Everywhere in the world, certain labs will have a standard where they actually measured it a lot of the times. So you measure that standard, and if your machine measures the exact same age, then you can use it for your own samples, okay? Because you know that the machine is calibrated right. The last thing we want to talk about is the fission track dating. The fission track dating is when you prepare a sample, a thin section of a rock. Anytime the uranium leaves the K-feldspar crystal, it will leave a low damage in the crystal. See, these are low damages, which is present the decay of the uranium atom. Okay, so they prepare a thin section. It has to be a highly polished thin section. You put it under the microscope and X and Y axis, and then you start counting low areas which was damaged by the alpha decay of the uranium atom. You see? Then you have to send the sample into a nuclear power plant where they force decay the leftovers. So basically, they force decay all the radioactive parent isotopes. And when they force decay those, they send the sample back and you have to recalculate. So when you recalculate the amount which is more than it originally was, it's going to give you the parent atoms, and the original number is going to give you the daughter atoms because those uranium atoms decayed, which left the damage. And after the force decaying, you have more because all the ones which are still uranium are going to decay because they bombard the sample, and all the uranium which is still present is going to decay. So the amount of after the force decay and before the force decay, you will get the parent isotopes which are still present versus the daughter isotopes. So it's complicated and very tedious work, but you're gonna get the same kind of ages as from the previous work. So let's look at a cross section and see how do we use this absolute age data. Remember, I told you that on sedimentary rocks, we cannot get really good data, that the best type of rocks we can use for absolute age dating are the igneous rocks. So here we have a cross section with Paleocene sedimentary rocks like limestone and sandstone, Eocene shale, and Oligocene sedimentary rocks. We have a couple of igneous rocks. This is a really good situation because you can tell exactly what happened when. We have a lava flow here, which is 20 million years old. Another one, which is 30. We have a dike, which went through only the Paleocene sediments, and it's 57 million. And then another one, which went through all the way to the Eocene sedimentary rocks and got eroded right there. And this is 36 million years old. So what we know here is that the older dike didn't go through the Eocene, so therefore the Eocene sedimentary rocks were not there yet. So what we know that these guys, the Paleocene sedimentary rocks, are older than 57 million years. The 36 million year old dike went through the Eocene sediment, so we can tell that these guys are younger than 57, and older than 36. Why? Because 36 went through them, so they had to be there. And also older than the 30 million, obviously, because that didn't go through it, but it was already there because it flew on top of it. Now, what do we know about the Oligocene sedimentary rocks? We do know that they are younger than the 36 and definitely younger than the 30 because it was before that. But what we also know that they are older than the 20. So we can put this Oligocene sedimentary rocks between 30 million and 20. And that's the only thing we can do. Which in my book, it's pretty cool. Like in geology, that's a pretty good age dating for sedimentary rocks, and that's the best we can have. And I hope you enjoyed this presentation, and I will see you in the next module. Bye.